Hello, this is the next video in a playlist that I'm calling Probability Measure, and here we're going to look at the unique extension of the Lebesgue-Stieltjes measure on the Borel sets. Now, here are the steps to extend the Lebesgue-Stieltjes measure that we've taken so far. And if I have a P, it means a previous video, and N is a new video. So in step 1, this was a previous video. We defined on all the right semi-closed intervals, say A to B, where A and B are real, this measure, mu of AB, which was f of A minus f of B, where f is an increasing right continuous function. And this was the Lebesgue-Stieltjes measure. Now, then in step 2, we extended mu, the Lebesgue-Stieltjes measure, to a field generated from the right semi-closed intervals. Now, if we let I1 through IK be disjoint right semi-closed intervals, then we define this new measure, the measure of the union of those disjoint intervals, as the sum. And then we noted that mu is sigma finite on the field generated by these right semi-closed intervals. For all n, mu of minus n to n is finite. And as n goes to infinity, it is r. So it is sigma finite. We then extended mu to a field of, including the closures of the real numbers, where that really means it's r plus, and then we add minus infinity, infinity. And this is mainly for convenience. And we showed that mu is countably additive and extended it to this extended real numbers mainly for convenience. But then, as a new step, we needed to find an outer measure on all subsets of R in this fashion. So let's let E be any subset of R. Then the measure of that set E is the femum of mu of the intersection of all these right semi-closed intervals, such that E is a subset of this. So we take all possible sets of right semi-closed intervals, find the measure of each one of them, and then such that E is a subset of it, and then we take the smallest, and then that's going to be the measure of E. It's the outer measure. Now, if we restrict mu star to the sigma field generated by these right semi-closed intervals, which is the Borel sets, then by Carathéodory's extension theorem, mu star is the unique extension to the Borel sets, and we'll just call mu star mu. And really, mu star is mu when we're within the field generated by the right semi-closed intervals. They are 100% equal. Or if we just look at a right semi-closed interval, they're 100% equal. It's when we extend it to the reals, all subsets of the reals, or restrict it to this sigma field, then we have to use this measure here. And by Carathéodory's extension theorem, it's unique. And I have a theorem where we prove this step. Now let's look at some of the measures, Lebesgue-Stieltjes measures on all types of intervals in the Borel sets. And so if we look at, A to B, where it's right semi-closed, this, the definition of Lebesgue-Stieltjes is that it's f of B minus f of A, where f is a distribution function. If we look at the measure of the open interval A to B, that's f of B minus f of A. And B minus is really, it's the limit as we approach B from the left. That's what B minus represents. Sometimes it's easier to see it like this, that f of B minus some small number, where epsilon goes to 0. This is the same as f of B minus. And then the measure of A to B is actually the limit of the measure of A to B minus n, right? This set, as n goes to infinity, is the open interval A to B, right? But the measure of this right semiclosed interval is f of b minus f of a. But as the limit goes to infinity, this is f of b minus. It's the limit as we approach b from the left side or the negative side. Now, mu of the closed interval a to b is the limit of this, mu of a minus 1 over n, for example, and then b, right closed, and then this measure is, f of b minus f of a minus n, but this is f of a minus. We're approaching a from the left side. So that's what this is equal to. Now, mu of a to b, where it's closed and open, is going to be the limit of mu of this interval, a minus 1 over n, b minus 1 over n. This limits to this. But this, using Lebesgue-Stieltjes measure, is this, f of b minus minus f of a minus. Now, if we look at the measure of a point, then that can be thought of as the limit as n goes to infinity of the mu of this interval, right? In limit, this interval goes to that point. But this is f of, f of x minus f of x minus n. As the n goes to infinity, that's f minus. Now, notice that if f is continuous at x, then this measure is 0. And this is one of the sole reasons why Lebesgue-Stieltjes measure was developed. The Lebesgue measure of any point is always 0. But the Lebesgue-Stieltjes measure allows for points to have a measure or a probability. Now, when a goes to minus infinity or b goes to infinity, these intervals can be defined similar up here. It's mu of minus infinity to b can be thought of f of b minus f of minus infinity. This interval, the measure of this open interval, but can be thought of this, and we'll go fast because it's really repeating what we've done up here. Mu of a to infinity is f of infinity minus f of a. This interval is, from a to infinity is then f of infinity minus f of a minus, so as we're approaching a from the left side. And the measure of the real numbers is, is f of infinity minus f of minus infinity. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.